Hello everyone, I am Sunanta from SNS College of Technology, Department of Mathematics. As the continuation of the lecture series in eigenvalue problems, we are going to see properties of eigenvalues and eigenvectors in this video. So first is introduction to eigenvalue and eigenvectors. So definition is for a square matrix A, if there exists a scalar lambda and a non-zero vector V such that AV equal to lambda V, then lambda is the eigenvalue and V is an eigenvector of A. Here the importance is fundamental in linear transformation, stability analysis and engineering applications. Next is finding of the eigenvalue. So as we have seen already, the characteristic equation is framed from the matrix by subtracting lambda from the A. So determinant of A minus lambda I equal to 0 is the characteristic equation. For example, if we have a matrix A equal to A, B, C, D, then the characteristic equation is given by A minus lambda I can be given by A minus lambda, B, C and D minus lambda. So on taking the determinant of that matrix, we will get lambda square minus A plus D into lambda plus AD minus BC equal to 0. So which is the characteristic equation of the given matrix. Next is we are going to see the properties. So first one is a property, sum of eigenvalues is equal to trace of A, which means trace of A can be found by using lambda 1, lambda 2, etc. up to lambda n. Next is the property 2, which is product of eigenvalues is equal to determinant of A. For example, in a matrix which can be given by determinant of A is equal to lambda 1, lambda 2, lambda 3, etc. up to lambda n. For example, if I have a matrix A equal to 2, 1, 1 and 2, then using the first property we can write trace of A is equal to 2 plus 2, which is 4. And on finding the property, on using property 2, we can write determinant of A is equal to 3 by using lambda values. Using characteristic equation, we can find 2 minus 2, 2 into 2 is 4, minus 1 is 3, so which is 3. Next is property 3. If A is invertible, then eigenvalues are non-zero and eigenvalues of A inverse are 1 by lambda 1, 1 by lambda 2, etc. up to 1 by lambda n. Similarly, property 4 is similar matrix have same eigenvalues. For example, B equal to P inverse AP. Then B and A share the same eigenvalues. Next is Cayley-Hamilton theorem. Every square matrix satisfies its own characteristic equation P of A equal to 0, where P of lambda equal to determinant of A minus lambda I. Next is property 5. Eigenvectors corresponding to distinct eigenvalues are linearly independent. Next is property 6. For a symmetric matrix, eigenvectors corresponding to distinct eigenvalues are orthogonal. For example, symmetric matrix means when we transpose that, we will get the same matrix. So therefore, if we have 1, 1, minus 1 and 1, then it on turns we will get the orthogonal eigenvalues. Next is diagonalization definition. A matrix A is diagonalizable if A is equal to PD P inverse, where D is the diagonal, that is, will have only the diagonal elements. In diagonal elements, lambda values are placed and P contains the eigenvectors. Next condition is A must have n linearly independent eigenvalues. Now let us consider the example problem in which the eigenvalues and eigenvectors of A are asked to find. So using our first property, determinant of A minus lambda I is equal to, which will be given by 2 minus lambda the whole square minus 1, which in turns will give the equation lambda square minus 4 lambda plus 3 equal to 0. Next, the eigenvalues of this matrix is 1 and 3. So from this we can write for 1, when we substitute 1, we get 1, 1, 1, 1. So V is equal to 0. So when we solve this, we will get the first equation vector corresponding to lambda equal to 1 as 1 minus 1. Next, when we apply lambda equal to 3, we get minus 1, 1, 1 minus 1. So when we frame this into an equation, we get minus 1x plus y, x minus y. So on solving that, we will get V is equal to 1 by 1. So here the eigenvectors are orthogonal, that is 1, minus 1, 1 and 0. Next is the applications of the eigenvalues and eigenvectors, which are in engineering field we can use vibrational analysis and stability of structures. Next, in biology, we can use Leslie model, so in which we can find the population growth or population decrease rate. Next, the dominant eigenvalue will give the growth rate, and the minimum value will give the decrease rate. Next, the eigenvector will give the stable age distribution. Then in physics, it will give quantum mechanics. This eigenvalue and eigenvectors are used. Next, in data science, principal component analysis is used. Thank you.